So the last time we finished by proving proposition about lifts. So let me remind you what was it. So there was a proposition. There, so to summarize, there was exist unique lift of tilde such that the following diagram was commutative. The diagram was as follows. So we had a fixed map from topological space Y times an interval with X. X was covered by X tilde. And so we also consider embedding of Y itself into Y times interval by just taking this, by just taking 0 in the interval. And we also had a fixed, so yeah, this was F. And we had a given lift, a fixed lift of a restriction F to the beginning of the interval. And the question was about existence and uniqueness of our full lift of F of tilde, which is consistent with this lift of a restricted function. And, okay, so this is what, so there was a long proof of this statement. So also let me remind you, so what there was a bit of confusion about definition of this covering, but we finally agreed that it should be the following. So let me remind you, so the cover basic points, so it's covering space X tilde is such that so there's a map, it comes with a map, equipped with a map from X tilde to X, continuous map such that any point X in topological space X, there exists its neighborhood. So open neighborhood such that its pre-image is a disjoint union. Hope you're familiar with this symbol. So this means a union such that any pair of sets here are disjoint. The disjoint union of sets UX alpha, and indeed we want to require them to be also open, otherwise this proposition would fail, we wouldn't be able to prove it. And moreover, if I restrict P on one of the guys here for some alpha, it provides me with a homomorphism to the original neighborhood. So this is a reminder. Now, so there are two important particular cases of this proposition which will be important for us. So let me formulate the first corollary of this proposition, corollary 1. So this is immediately follows in the general case if I take Y to be a point, and this statement, so the statement, this general statement when Y is a point can be reformulated as follows. For any box from an interval So pass is a map from in interval to some topological space X, such that let's say the fix it's start to be x0, and the fix, and we also want to fix a lift of x0 meaning that p of x0 tilde is x0, and then the statement that there exists a unique pass f tilde in the covering space x tilde such that it's a pass starting from my fixed lift x0 tilde. So what does this mean geometrically? Here, some topological space X, so it's lifted to x tilde, which is subjected to X, and if I choose some pass, so fix choose some pass starting from x0 here, and fix particular lift of x0, point x0 in the cover, then it means there is a unique, okay, let me draw something more less generic, something like this. There exists a unique lift f tilde in the cover. So once I fix a pass in the bottom and fix it's enough to fix the lift of a start point, so that we have a unique lift. Okay. So this corollary just immediately follows from the general proposition, and we also will need the second corollary. So this will follow from the proposition, from the general proposition when y is an interval, but it will require some additional comments. So the statement which you want to make is that for any path homotopy f is the path homotopy in topological space X, and a fixed again, we fix a lift of some point x0 in the topological space X. Such that so since it's a path homotopy, it's so we know in particular that if I restrict myself, so if I so for any so T is a homotopy parameter. For any homotopy parameter, if I restrict myself in the to 0 here, it should be should be a fixed point, like 0. And the statement is then in this under this assumption there exists a unique path homotopy F tilde in the covering space so this will be a homotopy between paths starting at 0, while the original homotopy was between paths starting from like 0 without tilde and lifting
question, how are we sure that this P minus 1 is well defined?
Sorry, thanks. Fix. Sorry. So we fix, yeah, this is just any zero in the lift in the covering space such that is projected.
So it is P minus 1 of the big X.
No, this is just a single point. This is a pre-image of a single point. Well, you can maybe it's better for it. So again, so suppose you have some path homotopy between a couple of topological spaces, between, let's say, F and some path, another path F prime, and the statement that it's lifted, uniquely lifted, the path homotopy in the covering space, again, assuming that we fix the lift x0 tilde of the starting point. So again, this is more or less immediately follows from the general proposition. So here I want to take so this will be, so in terms of a general proposition, this will be my Y, the topological space Y will be an interval where my homotopy parameter lives. So let me, so in this case, okay, let me write the formula. What is actually the proof of the statement? So we know by the statement, so this is a restriction so restriction of the lifted homotopy to S0 is fixed. Sorry, what I want to, so when S is equal to 0 and take any point in Y here and I restrict in my interval the first point to be 0. So we know this is fixed, the definition is fixed to a constant map to 0 tilde. So this is what in the general setting was denoted by F 0 tilde. and therefore there exists a unique lift F tilde of F. But we also, we need to, so this gives me some function from interval times interval to x tilde, which lifts, which is projected to the original F. But we need to verify that this is indeed a path homotopy. So it may happen, in particular, it may happen that so this is lifted, but the endpoints, this is not a path, you know, the path homotopy should satisfy the additional condition that if I restrict my path parameter to 1, for any t, this should be the same. In order for this to be a path homotopy. So it may happen in principle that the endpoint, so this is uncorrelated, but these endpoints, they become separated, although they projected to the same endpoint here. But this actually cannot happen because so we have to verify it should be the same for any t. In order for this not just to be any function from a square to x tilde, but this should be a path homotopy. It should be the same, but this follows from the fact that this function is a function of the fixed one here, because it is a function of the second argument, is a lift, is a unique lift of F1 dot, and which is a constant map to so we know that F, the original F was a path homotopy, so the constant map to so there's a constant map to some point here, and we haven't specified what exactly it denotes any point. This is a constant map, and we know that if I choose so the constant map can be lifted to a constant map. And since we know it's a unique, so this can be applied, so here we apply parallel first. By considering this is some paths. So we know that if I understand this is a path here in x, which is a constant path, staying just at this point, we know that there's a unique lift, and we know the constant path can be always lifted to a constant path. And then by uniqueness, this should be also constant. So those points cannot be separated. Questions? So now we are prepared to prove the announced statement about the fundamental group of a circle. So there was more elaborated proposition which I already stated before, and now we actually are prepared to prove it. How do we do this? So essentially, we want to construct explicitly this isomorphism. So let me take f to be a particular loop in S1, which we agreed to by default present as a quotient of R by Z, and we want this to be a loop starting and ending at 0. And so now we can use corollary 1, we just formulated. By corollary 1 there exists a unique lift f tilde in the following diagram. So we have original map. Original f was considered the map from the interval to S1, which is covered. As we discussed, an example of a cover was R, and the projection map is just taking element of R modulo 1. Consider it's up to an integer, and the lift f tilde is such that this composition of this map with projection is the same as f. So by corollary 1 is there exists lift like this, but we also need to ensure uniqueness, we need to fix an initial value, and we can fix the initial value to be 0. So this is correct. This is a value choice because 0 is of course projected to 0. Well, maybe to be more precise, I need to put a bracket here. So it's an equivalence class of this real number modular integers, and of course 0 is projected to its class. Okay, and so what about the endpoint of the lift? So we know the endpoint, the projection of f tilde of 1, it should be the same. So by definition of the lift, it should be the same as f of 1, and this should be again a class of 0. But we know that the only elements in the real line which are projected to the same class, because the same element here as 0 are integers. So it follows that f tilde of 1 should be an integer. So understand integers as a subset in R here. So again, you can visualize this using the picture of this lift which we had before. You can imagine it's S1 like this, and the R sitting above it, sort of infinite spiral. Projection. So morally, what happens if you have some path here, and suppose it's example goes path f, it goes at once a number of times, starts and it's at 0. So this path is lifted. So I fix my suppose this is a fixed 0 in R. This is 0 in R. And I start lifting it, and it goes like this, so the unique lift, and it goes a few times. And it ends up somewhere here. And it goes, so this integer denotes how many floors go in vertical direction of this lift. Okay, but I mean, formally it goes like this, and then it allows me to define the map alpha from pi1 of S1. So I fix my base point to be 0 here to Z. It's okay. It's a class of 0 in this quotient, such that the class in the fundamental group represented by my loop F is mapped to this integer here, F tilde. So this defines me, at least naively, this defines me somehow, but of course I need to check something. I need to check it's actually well defined. So again, as usual, I need to check the independence of the choice of representative in this class. Few remarks are in order. Well, okay, I mean, this remarks part. This is part of the proof. So the alpha is well defined. To show this, let me take any other path F tilde, which is path homotopic to F, and we want to show that it's mapped to the same number. So the path homotopic, there exists some path homotopy F, and by corollary 2, there exists a unique lift of this path homotopy. So this is a lifted path homotopy. F tilde, and which is will realize path homotopy between the corresponding lifts. So both lifts, we need to, in order for this lift of path, in order to, for the assumptions of the corollary tube to be satisfied, these both lifts should start at the same point, which we chose to be 0. This is a homotopy between paths in R, and okay, but then since this is a path homotopic, so we show that F tilde is indeed path homotopy. In particular, so we show that the end points here should be also the same. Otherwise, it wouldn't be a path homotopy by definition. And then, by definition of this map, the value of alpha is indeed independent on the choice of representative. Okay, so this is well defined. So, but we also want it to be not just arbitrary map, we want it to be a homomorphism. Group homomorphism, and So to show that, we need to verify if we take some other class here and multiply this. This will go into group operation here in Z, which is addition. Okay, so take, let me take G to be other group in a circle, which again starts and ends as a class of 0 in this one. And so by G tilde I will denote unique, as you know it's unique, lift of G such that it starts at 0. But I also consider, it will be useful when we consider a different lift, which I will denote G tilde prime. And it's also will be unique, but now I will require, I need to choose, I will choose a different initial point, and I will choose a point such that it's the same as F tilde 1. So it's consistent because they are projected, this is still, since it's an integer, is projected to the class of 0. So since, so by uniqueness, I can deduce that they're simply related. So I can also, I know that if I write the following function, G tilde of S plus constant which is F tilde of 1. This will satisfy this condition. So since this is integer which is projected to 0, this will be also a lift which satisfies this condition, such initial condition. But because of uniqueness, it should be the same. So we have the following explicit relation between those two different lifts. They just differ by some constant. And okay. So I want to check that this is a homomorphism. I want to consider what will be the value of alpha on a product of a class of F times G. So here it's a group product in phi 1. So by definition of the group product in phi 1, this should be the same as alpha of class of G composed with F, and by my definition of alpha here, this should be the same as, so the lift of this composition at 1. So this is the definition of alpha, and so we know that so so the lift of the composition it's the same, is up to homotopy. It's the same as a composition of F tilde and G tilde prime of 1, right? Because this indeed provides me a lift. It's easy to see that it provides a lift of the composition because the start point of G tilde prime is exactly chosen to be an endpoint of F tilde. But then I use this formula, and so first so because this is a lift, so we need just a value of 1 of this path. So the value at the endpoint is the same as the endpoint of this function. The value of this function at 1, and then I just use this formula, and this gives me G tilde of 1 plus F tilde of 1. which is indeed the group operation. Here, mainly this is alpha class of F plus alpha plus H. So indeed this map respects group structure, but we want to check that this is isomorphism. So one way to check that this is isomorphism is to check that this is both surjective and injective. So let's first check that this is surjective. Surjective means that any integer here can be realized as an image of a certain loop, of a class of some loop. So let me take an arbitrary integer m, and I want to present a path which realizes this integer here, and I can take explicitly f of s. This is a path to be a class of ms. So this element. So inside we have an element, the real line, and this is the element. So here is a class is just a class with respect to quotient of integers. And then, of course, I can immediately deduce what should be a lift. The lift is just ms, so it satisfies the condition that it's projective to this for any s, and it starts at 0 when s is 0. And it also satisfies the condition that so we know that the value at 1 is m, and then it follows, by definition of alpha, it follows that the value of alpha on a class of loop f is m. For any m, we found the preimage. So this proves that this is surjective, and now we want to show that this is injective as well. So to show this injective, we so let me assume there are two. Let me take some two classes, any two classes, pass f and g, and I want to show that this condition implies that the class is actually the same. This will show my this is injective. So by definition, this equality implies that the value of a lift of f at 1 is the same as the value of a lift of g at 1. But then, so if this is the case, then I can realize a path homotopy. I can explicitly give you expression for path homotopy between path f and path g. So this is a path homotopy inside this one. This is the class model 1, so this is an element. The whole thing is an element. Next one. And this is by construction, this is a continuous function, and indeed, if I take t to be 0, it's the same as G tilde of S, G tilde of S mod 1, which is the same as G of S. Because we know that G tilde of S mod 1 for any S is the same as G by definition, and but just by definition of G tilde, which is a lift of G, and F tilde of S mod 1 is the same as by construction, and therefore this is indeed a homotopy. So the path homotopy between F and G. Therefore, the classes in pi 1 are the same, and therefore therefore alpha is isomorphism. So since alpha is injective, and from which it follows. So we already know that alpha is surjective, that and follows that alpha is an isomorphism. We have an isomorphism between pi 1 and z, which we explicitly constructed. So this is almost everything we want to prove, but there was a part of there was additional statement in the full statement about proposition that so there was a pass. So remind you in the formulation of the proposition there was also a pass like this, which send it S to just S mod 1, and there was a statement that this path should be mapped to a generator of Z, and we know that indeed alpha omega is so here I can take the lift omega tilde just to be S. And alpha of omega is omega tilde of 1, which is 1. So indeed, omega alpha is generated.
Any question?
Yes.
The definition of the fundamental group. In the case where X is a subset of the Euclidean of Rn,
Yes.
can we just take the differentiable loops? Basically the same thing.
Well, it depends what kind of subset.
Like S1.
Yeah.
So in that case, what I
I
want.
mean, if you have something like manifold, you can always
Yes,
do
differential
one.
ones.
Yeah,
Something
you can
different.
consider different.
Yes. In that case, in the case of S1, what I wanted to prove that if I take two loops in S1 with different, if they are homotopic, then they have the same winding number. I take the geometric circle, I take two, I want an equivalence between being homotopic and having the same winding number.
What is the definition of winding?
Is the integral, if I take loop 1, I take the integral 1 over 2pi with the integral,
Okay.
and I want to use the homotopy to prove that those two integrals are equal.
Yes.
Is this possible?
Yes.
Easy?
Well, yes, very easy. Because essentially this, well, you can define, you can relate this, if you, well, roughly, if you want to use something like this, I guess.
Yes, we will see. Yes.
Go like this. This gives you some log. And basically the argument log of z, if I do indefinite integral. And the argument of this log of z is it provides you the lift.
Yeah. In that case,
it provides you the map to this R which is lift.
And also, if we take two loops and we take the concatenation, the composition of the two loops, then the winding number is the addition.
So, it's
so why we can just use this isomorphism. We take each loop, so it's winding number.
yeah, but I mean, this is just a different way to realize this. I mean, you can explicitly by explicitly realizing this lift. Well, you have to, yeah. But also here we do some more general. We don't have assumption that this is differentiable. Other questions?
Yes. How to understand the representation of S1 as the quotient by Z?
Well, for example, like this, but I mean, it's so you have R, and so you want to impose this equivalence relation. With points R, but using this equivalence relation, you can always can find there is unique so for any t in R, you can find there exists let's say t0 in the unit interval such that t is equivalent to t0 plus some integer, right? We can always find a shift so that we can just up to this equivalence method, we can always push any number here to a unit interval, right? Just like this. And moreover, it's there is a unique t0 in the unit interval. It shows like only up to ambiguity, so between 0 and 1. So what I want to say is that R divided by Z is can be identified. There's homomorphism of this to just an interval where 0 and 1 are identified. And this is the
but what
this
does
is the one way to understand.
what does this representation assume? Because these two pairs are not homeomorphic each to other.
No, sorry. This is homomorphic to this.
No, I mean S1. Oh, S1 is homeomorphic to this with this relation 0,
Is it
1. Oh, okay. But not the full 0, 1.
But I mean, it depends. What is your usual definition of S1? If you define, if you want to define S1, for example, I don't use a alternative definition of S1. Define it by some sort of subset in R squared defined by this equation. Suppose you want something like this, but then there is you can find the explicit homomorphism, let's say phi, between this topological space and S1 defined like this by sending S, so the class of S here to to the pair point, which is cosine p bar s and sine p bar s.
Or just we can use the isomorphism here. We can, if we see S1 as subset of C of the complex, so we can take the isomorphism, taking t to exponential of it.
Yeah, I mean this is
Yes,
the same.
and the morphism is 2 pi z, so that's z, so take.
I mean this is the same, just very low dimension. So you can show that this is first of all one-to-one correspondence, and it's continuous. It's essentially just how you can, I mean, just the fact that the angle is defined modulo 2 pi. Okay, so this was first example of non-trivial fundamental group, and already this kind of simple statement allows to prove some kind of important theorems. So this will be the next two theorems will be the application of this result as a fundamental group of S1 first is what is usually called Brouwer fixed point theorem. Yeah, you can also another application which I'm not going to mention, I'm not going to consider this succeed, but one can also prove the fundamental theorem of algebra using fundamental group of S1, and there indeed it's I mean the proof is in many senses analogous to using this index, in the notion of index. So Brouwer fixed point theorem is the following statement. So for any, let me consider any continuous map from disk to itself. So disk I realize as a subset in R2 defined this is a closed disk defined by this condition, and so suppose I have any continuous map, the statement that there always exists a point in the disk such that h of x is the same as x. Proof. Suppose it's not true. Suppose for any assume that h of x is not equal to x for any x in my disk, then it follows that I can define the following continuous map. Or you map from disk to S1, which I can understand as a boundary of the disk. So here actually I'm using the fact that S1 is realized as this, but as I mentioned, just here there is a direct, there's explicit canonical homomorphism. These two topological spaces. So you can just consider since there's a canonical homomorphism, you can just consider them the same. Okay, so how do I define this map? So I will explain it to you generally. So the disk looks something like this. And so suppose I take some point x and I need to tell you what its value in a circle, what the value of this function r of x on a circle. And it will be constructed like this. So suppose h of x is the value of my function h on x. So it's not by my assumption doesn't coincide with x. So what I can do, I can draw a ray starting from h of x and passing through x, and this ray intersects the boundary for disk at some point, which will be the value of my map r of x. This is how I define this map, which will be continuous by construction, and moreover, we know that. So if x, by construction, if x is on the circle, this map becomes identity. So if I put x on, if x is on a circle, r of x is the coincide with x. So r of x is the same as x. X is in my boundary circle.
R is oh no, okay. D2 is closed.
Yeah, this is this boundary. And then by definition, R is a retract. We define the retract of disk onto its subspace S1. And so let me then take any loop f in the circle such that so it starts and ends at some fixed point x0 in this one. And then we can notice that it is contractible. So I'm not sure if I already mentioned this word. So contractible just means it's homotopic to a constant loop. Say 0. Or sometimes you can also find the term non-homotopic. Non-homotopic means it's homotopic to a constant loop. It's contractible in D2, so I can also understand by embedding S1 in D2, I can understand this loop in D2. So why is it contractible? So this is just by the existence of a linear, for example, you can take linear homotopy, which we already considered before. So it's compatible by the following explicit homotopy. So pass homotopy F valued in D2 defined by the following explicit formula. So S and T is sent to 1 minus T times F of S plus T. So again, I use a linear vector space structure in R2, so I can do these operations. And you see that when T, as before, when T is 0, this is f of s, and when t is 1, this is just a constant in 0. Okay, and but then, since we found the retract, by our assumption, we found the retract from d2 to s1, it is also contractible in S1, if we understand this is just purely S1, by homotopy, which is a composition of R and F. So now it's homotopy valued in S1. And so indeed, this is if I take this as a continuous map such that if I evaluate it on S0, this composition of R f of s, which is so since R restricted to S1, where f of s is valued, is identity, so it's the same of f of s. And I also need to check that this is a constant loop, and indeed it's a constant loop because x0 is a fixed point in S1. But then it follows that the class of f is trivial by 1 x and 0, s1. But this is, you know, it's isomorphic to z. And f was arbitrary loop in S1. So we showed that any loop is in S1 represent a trivial element in the fundamental loop. So this is a contradiction. I mean, here we're not actually using the fact that this is z, but we're just using the fact that there is it's not a trivial. Questions? Here, so this statement is not so intuitively obvious that any map from disk to itself has a fixed point. But this, I mean, our technique, which we developed, provides a rather simple proof.
You can still generalize it to any complex, right?
To any what?
Complex.
Convex, yeah, sure.
But we need that the fundamental group is at least non-trivial, I mean, of the convex set.
Yes, on R2 or like that. Right.
Yeah, maybe.
Dimension 2, of course. Two-dimensional
Well,
complex of R2. And all the boundary is.
Yes. I mean, if we have convex region in R2, the boundary is homomorphic to it. Okay, second application will be the theorem of Borsuk. Also, of course, it's worth mentioning that all the, I mean, these are named theorems, but of course the original proofs were not exactly like this. So the statement is the following. So for any continuous map from S2 to R2, there exists so I here again, realize S2 just as a subspace in R3 defined by this equation with the norm is 1. So for any continuous map like this, there exists a point in S2 such that f of x is the same as f minus x. S2 is for this, so x equal to x minus x means antipodal point. So this is Earth, this is somewhere in New Zealand, and this is in Spain. We prove this. So again, the proof would be again by contradiction. So assume f of x doesn't equal to f of minus x for any x minus 2. And then we again will use this to define a certain continuous map by G. So this will be a map from S2 to S1. So S1, again, for simplify things here, we realize that the subspace in R2, as before, just a unit circle in R2. And the map is given by taking x and mapping it to the following. So this combines the vector in R2, and by contraction this would be a vector of unit length. This is well defined, and because of this assumption, this is well defined. This is well defined unit vector, unit length vector here. So this is condenses the element of S2. Element of S1. And also let me consider the following map eta from, so this will be a pass in S2, which is explicitly given by the following formula. So this will be a loop. So again, if my so the sphere looks something like this, so eta is just a loop which winds along the equator. Again, see the composition of those two guys. So first, you can see the map from the pass into S2, and then map it to pass in S1 by this composition. So this gives me a pass in S1. So it represents the remote that it's a loop. Is the endpoint and the endpoint's coincide. And So as before, since we do have a loop, if we have a loop in S1, we can define its lift H tilde, we pass in R, so it's a lift with respect to my projection. Well, here, so it's the same projection as before, but modulo the fact that I realize my S1 a bit differently here. So I realize my S1 as a subset in R2 satisfying this condition. So the projection map from R to S1 like this way will look as follows. So this element here S maps to cosine to S. But this is essentially the same. It's the same projection map as before. Just we use a different realization of a circle. And so by definition of so I erased my formulas, but you saw that so by definition of G, it satisfies this condition that G of minus x was minus G of x, just by the explicit formula which were there, and it follows that H of x of minus x is minus H of x. G was a map from S2 to S1, and it satisfies this condition. And so let me. So S1 looks like this, and okay, we have this condition, and we also had this condition that n of eta of s plus 1/2, just by explicit formula, is the same as minus eta of s. This was as you remember, this eta of s was just defined by a pair of the value of eta of s is a cosine comma sine of 2 pi s. So just satisfies this condition, and together with this implies that h of s plus 1/2 is minus h of s. It looks something like this. So here, S1 is considered to be element in R2, so just minus here means that they are opposite points. So this minus what this actually means. And so if I consider a lift of this guy, so on the level of lift, for a lifted path. This will imply, if you lift with respect to this projection, this will imply that this is the same as h tilde of s plus m plus 1/2 for some integer m. Because if I take left and right hand side of this equality and apply this function, I will get this relation. I mean, this integer just doesn't affect, so when you apply projection, the result is independent of this m, but this 1/2 here will result, the shift of this argument here by 1/2 is equivalent to the change of sign here. And okay, and this means, so if I use the same, so if I remember our construction in the proof that the fundamental group is Z, okay, so it's well, it's too early to talk about this. So first I want to make this statement. So in principle, M here could depend on S, but we know that H of S is continuous, and so M, if I express M from this equality, M will be a difference between continuous functions. But we also know that M should be integer for any S. So the only way to satisfy is it for M to be a constant, because you cannot have it's not possible to have a non-constant continuous function which takes integer values. I mean, it's a function which is considered to be a continuous function in R is values. So M is independent on S in this equality, and then I can use this equality to calculate the value of h tilde of 1. So so as before, I consider lift such that h tilde of 0 is 0. And then h tilde of 1, by this equality here, h tilde of 1 is the same as h tilde of 1/2 plus m plus 1/2. And I can use this equality once more, and I get, this is, actually I don't need, so h tilde of 0 can be actually anything. What is important is this is h tilde of 0 plus 2m plus 1 if I apply the second time. And then this means that the difference, what is important actually for us is the difference between h tilde of 1 and h tilde of 0. And this is equal to 2m plus 1. And so as we know, as we showed in the proof of the fact that phi1 of S1 is Z, this means that the class of the loop, the original loop H in S1 represents a class H represents 2m plus 1 in the fundamental group S1. It's the value between the initial value of the lift and the final value of the lift. And we know that this is non-zero for any m. For any integer m, this is non-zero. Because this is an odd number. It can be 0. And this means that H is not contractible. In S1. But H, remember that H was given by this composition of G and eta. And eta is contractible. In S2. This is obvious because you can, if you want, you can represent, you can find an explicit homotopy, but it's obvious that you can, there is a path homotopy which just constructs this loop to the point where you can continuously deform it to the point in S2. And of course I can use this position of this homotopy with my function, with my continuous function G to contract H. So again we arrived at the contradiction. And therefore our assumption is false. Questions? Questions? Okay, so then we continue to study first the properties of the fundamental group, which will allow, in particular, they will allow us to calculate for more complicated topological spaces. In particular, I want to show the following proposition. So assume X and Y are path connected. And then we want to show the fundamental group of Cartesian product of these two topological spaces is anamorphic. This will actually there will be canonical isomorphism, we will see, anamorphic to a direct product of the corresponding fundamental groups. Let me see if I can. Okay. So, well, this is more or less will follow from definition, but of various things, the definition of the product, and definition for the fundamental group, and so on. But to be more careful, okay, let me consider. So consider f to be any function from some topological space Z to to a product of these logical spaces. And so this can be specified by the value of its components in X, which I will call by H, and its component in Y, which we'll call G or Z. So where so H is some function from Z to X, and G is some continuous function from Y. Well, to be more precise, just by definition of the topology of the Cartesian product here, F is continuous if and only if H and G are continuous. It's a general statement like this. Now let me take a particular case, that to be unit interval. Then the statement means the following. So F is a loop in X times Y, such that, let's say, it starts and ends at X0, Y0, where X0 and Y0 are some fixed point in X and Y. So the statement is equivalent to the statement that G and H, so the functions H and G, which define my function F, are loops in X and Y respectively, such that G starts and ends at X0 and H starts at 0. And another case which you want to consider is take Z to be a product of unit intervals. And this general statement then means the following, is a phrase the following, a path homotopy in X times Y can be stood as a pair of path homotopies in X and Y. So in particular, if F is path homotopic to F prime, this means its components are path homotopics. Okay, we're almost done. So from this it follows there is a well-defined bijection between this product of groups and fundamental groups and the fundamental group of the product, just by taking a pair. So this is just bijection as between sets. So you take a pair of homotopy classes of path H and path G, and it's mapped to a homotopy class of a pair of a path here, which is realized by a pair of functions h and g. And this is independent of this is well defined and independent of the choice represented by these two statements. And moreover, it is a homomorphism. Which will, well, since it's a bijection, it will mean that it's actually isomorphism. So we need to check that this bijection respects group structure. So if I take a multiplication here, it will map to multiplication to a product of element here. And so let me do that. So let me take a pair of elements here. So this is one element of the product and the other element of the product. So if I multiply them, then so it's just by definition of the product structure in this in the direct product of groups, I need to multiply just the corresponding components. And for multiplication of components, we know that this is just this corresponds to a composition of paths. So it's just by definition of the direct product of the group and the group structure in the fundamental group, it's the following. Here, and by this bijection, it corresponds to a class of a pair of paths obtained by positions like this. But now we can use the definition of the product structure here, and this is the indeed the product of the corresponding classes here. Because if you want to, so by definition we need to compose these two paths in the product by the composition of the two paths in the product corresponds to just composing the components. So we indeed check that the product of elements is mapped to a product of elements. So this is means that this is an isomorphism. Okay, stop here.